So I know that a lot of you have talked about the scientific method at some point in some science class somewhere, and you're going, oh gosh, I can't believe we have to talk about this again. But this is actually something that is really critical to what the sciences are and what biology is, because without the scientific method, there's really no formalized system for studying the sciences. So the development of this in, I believe it was about the 1600s, is a really big deal. Because before that point, things were not real codified, if you will. Different people would do things in different ways, and it made the verifiability and falsifiability components of studying science really tricky, because people weren't all doing things in the same way. So this is a major development. And basically what the goal here was to create a codified system of studying biological concepts and doing research so that when we got to the end of things, we would have reliable, consistent data to work with. So the first step in the scientific method is the observation step. And I really think this is what makes scientists unique amongst the people on this planet, is that they are just uniquely curious about what is going on in the world around them. They really are interested in what is happening, why it is happening, how it takes place. And so the first thing you do is you make observations. I observe things like my cats eat differently in the summer than they do in the winter, because I got to fill the food a lot more often in the summer than I do in the winter. I make observations like, hey, you know, a lot of times when I get sick, I get a fever. I wonder why that is. And it's the curiosity. Now, do these all have to be mind-blowingly scientific things? No, they don't. I've had students who have told me about scientific method in terms of, oh, I really like to go to a bar with my buddy, but, you know, more girls always give him their phone number than they do to me. So I'm curious, why does he get so many more phone numbers from girls than I do? And we've done whole examples of scientific method around things like that. You know, why are my kids more energetic when they drink Mountain Dew than when they drink Sprite? Why am I in a better mood when it's sunny than when it's cloudy? And so it's really just about being aware and observing the world around you and wondering. That's a good trick for all of us. Once you've got that sense of wondering in your mind, the next step is to do a little research, find out what you can about that concept. Has anybody else ever experienced this? Has anybody else ever researched this? And based on that information that you gain, you make an educated guess to explain your observation. This educated guess is referred to as a hypothesis. A little thesis, a small idea. And what's key to understanding hypotheses is that they're not the be-all and end-all of your research. They're a jumping-off point. And so usually when researchers are forming a hypothesis, they form not just one hypothesis, but several hypotheses, because very often there are many possible explanations to their observation. The key to forming a good hypothesis, however, is to focus on variables. Variables are things that can or do change in a system. They are things that change, they vary. And so what a hypothesis does is it uses one variable, it's called the independent variable, to explain what is going on, and another variable, called the dependent variable, to measure the result. So some examples of hypotheses based on some of the observations I made. If I observe that my cat eats more in the summer than in the winter, I might think about my cat. Well, my cat likes to run around a lot more in the summer and likes to go up and down stairs, looking for a flat house. So maybe he's more active in the summer than he is in the winter. And so maybe his hunger level and how much he eats is directly related to how much activity we get. Now, I could make other guesses. I could go, well, in the summer it's hotter than it is in the winter. Maybe it's about body temperature. Now, are there links between body temperature and activity level? Yes, there are. So there are potentially confusing things here, but I'm going to focus on one thing at a time so that I don't let temperature get in the way of activity and vice versa. I focus on one thing at a time. If I want to study both those things, then I need to do two different experiments. Another example, if I observe that when I'm sick, I get a fever, maybe based on things I can find out, I think, well, maybe fevers kill germs. And so maybe body temperature destroys germs. Now, could it be something else? Yes, maybe body temperature stimulates my body to mount a more effective defense against germs. Maybe some infectious organisms have chemicals or toxins that cause my body temperature to change, and it's not a choice on the part of my body. It's a reaction to being sick from those organisms. Turns out that in real life, all those things are actually true. But if you focus on one thing at a time, that'll give you an opportunity to explore that and exclude other possibilities for a little bit, and then you can come back and try to put all the pieces together at the end. So now it's time to devise an experiment. Experiments have variables and groups. And there's three kinds of variables. First one's called the independent variable. It's the thing you change, and it's the thing that explains the phenomena. So, if I'm going to say that the reason you get a fever when you're sick is because temperature kills off germs, then I'm going to change the temperature in the human body and look at how heavily infected tissues get. Something like that. Maybe I could have some old petri dishes and warm them up to different levels and find out if cool petri dishes are easy for germs to live in and hot petri dishes are hard for germs to live in. Something like that. Then you have the dependent variable. Well, how am I going to measure the effectiveness of my temperatures on their ability to kill germs? Well, in that case, it's probably pretty simple. I just need to count how many germs there were when I started and how many of them survived. So something like the 10 surviving colonies of germs or something along those lines. If I wanted to do this with my cat, maybe I say, okay, it's about activity level. So I'm going to put my cat on a little kitty treadmill, and I'm going to have, one cat that just gets to lay around on his pillow all day, and I'm going to have another cat that has to be on the treadmill for 2 hours a day, and then another cat that has to be on the treadmill for 4 hours a day, and then another cat who has to be on the treadmill for 8 hours a day. And so my independent variable is activity level in hours of treadmill time, and my dependent variable is going to be how much food they eat. So I'll measure how much food they eat. There's one more kind of variable in the mix here, and it's called a control variable. Control variables are things that stay the same in all your different experimental groups. And so, for example, if I'm going to study the germs thing, maybe I only want to study one particular bacterium, because some bacteriums might respond to increasing the temperature by dying. Some bacteria might grow more if I increase the temperature. Some bacteria might not care about temperature at all. So it'll depend on which bacterium I choose. I want to make sure I only study one bacterium. Same if I'm doing this in some kind of little petri dish, I want to make sure I only use one kind of growth medium or tissue to study on. I want to make sure that I choose only a particular strain of that bacterium or something along those lines. Lots of things I want to kind of regulate so that I can really focus on whether or not temperature influences those bacteria. I don't want to change salt levels or water levels or anything else but temperature. It's about focus. Controls let you focus. If you're doing the cat thing, maybe the controls are to only use male cats, to only use 5-year-old cats, to only use short-haired cats for the disease. Cats will be affected differently by changing their activity levels. And so again, it's about letting you focus on that core component of your hypothesis, which was activity levels for the cat. So when you develop this experiment, you're going to have what we call testing groups. And the first testing group is called the control group. It's a basis for comparison. So for example, if I'm going to test temperature and bacterial growth, the most basic temperature to test at would be normal human body temperature if I'm interested in growth in humans. So I'd start with 98.6. And maybe I would try cooler temperatures, and those would be some different groups. And maybe I would try warmer temperatures, and those would be some other different groups. But the control is the norm, or the average a lot of times. If I'm going to use the cat one, maybe I'm going to say that 2 hours a day of activity is the norm for a cat. And so that's going to be my basis for comparison. It's not always a zero. Some people assume that zero is always your basis for comparison. But the basis for comparison should be the most normal in a lot of scenarios as opposed to being an extreme. And sometimes zero can be an extreme for some scenarios. All those other groups, warmer, cooler, more activity, less activity, are called experimental groups. And those are the ones where that independent variable temperature, the activity level, is going to be manipulated to get at the answer to our question. So you run your experiments, you run those little T treadmills, and you get some data. And the way that most of us like to look at data, well, the way most of us like to deal with data is to get a visual interpretation of data. And graphs are great ways to show you kind of the trends of what's going on in a living system or any system. And so we often use graphs to try to portray information. Now the tricky thing about graphs is that they're easy to kind of manipulate and mess up a little bit, because depending on the scales you use on the x and y axes, you can get a lot of variation in the way that graph looks to you. You can stretch it and kind of flex it and make it look almost any way you want to. So while graphs are a nice visual way to look at things, they can also be a little bit difficult to work with because they're very biased if you're not being honest about your data. And sometimes that's completely unintentional. So when you look at a graph, the independent variable will always be on the x-axis, and the dependent variable should always be on the y-axis. A few times when people mess with this, and it really makes things kind of ugly. But that's the general rule. So you should be able to look at any graph in a newspaper, in a scientific paper, or article, anywhere. And they should be set up almost always the same way, with the independent on the x-axis and the dependent on the y-axis. Okay, so if graphs are biased, how do we get rid of bias? Well, statistics are the key to getting rid of bias. Statistics are mathematical analyses of the numbers, and really that's the whole reason we use statistics, is that they keep us from being biased in our interpretation of that data. Here's some examples of graphs. Here's a bacterial growth graph. I cheated. I didn't know what I was going to do about. Here's one for cat feeding habits. This does bring up a good point. Sometimes we use time instead of the independent variable if it's something that we measure over time. So if I was measuring cat feeding habits, maybe I would measure them by week, and then I could correspond that back to time of year and temperature at given times of the year. So maybe, the first 4 weeks of May and June and July, and something like this. Next step, look at your data, run your statistics, and draw some conclusions. There's only two conclusions that we generally draw in the sciences. One is that we could reject the hypothesis. We're basically just saying we're wrong. The hypothesis is wrong. And that's a nice, firm, solid place to be. I'm wrong. It's very, very definite. The other side is to fail to reject the hypothesis, which says, I'm not wrong, and I might be right. And it's kind of a tricky balancing act that we do. We're never real confident in our way that we portray our results in the conclusion. We always kind of couch it in terms like, this could be correct, it might be right, Because there's always other options out there. There's always other possible explanations. And you don't want to kind of put yourself in a hole and dig yourself a hole and get yourself in a corner and then not be able to have any wiggle room. So by being kind of tentative in our conclusion, it allows us to have some room for error in case we have either done something incorrectly or misinterpreted the results or just failed to think of something that could have altered our information. Next step, try to verify your results. And that's what a lot of biologists are really doing out there, is they are trying to spend time verifying the results. As you verify your results, your hypothesis starts to get upgraded. So we started out with this hypothesis, an educated guess based on previous knowledge. That hypothesis can go one of two ways. It can either become a theory or it can become a law. If you get lots and lots of supports and verification for your data. Theories try to explain how or why something is occurring. Laws describe events using mathematics most of the time. Sometimes there's no mathematics to describe the event with, but ideally you have some math to describe it with. So theories don't become laws, laws can't become theories. They're independent things. If you think about, for example, the theory of natural selection, it's an attempt to explain how or why evolution occurs. It's actually not debating the core components of evolution. Evolution says that organisms change and that organisms come from one another. Some of us aren't very comfortable with that, but the reality is most people have to admit those two things when it comes right down to it. The question is how or why does that happen? And that one organism develops another organism with a little bit of why as well. And so that's kind of the touchy subject. And it's funny because most of us aren't all that uncomfortable applying evolution to other organisms. But when you start trying to apply it to humans, all of a sudden people get really upset. And I'm not trying to disrespect that perspective. I'm not going to ever tell you what you should believe. I'm not going to debate with you religion versus evolution. However, there is a lot of support out there for evolution, and it's just an attempt with a lot of support to explain how or why organisms are capable of changing and developing in the ways that they do. Laws, on the other hand, are much more set in stone. The law of gravity would be a good example. It describes how things are attracted towards organisms that rotate. The Earth spins, right? And because the Earth spins and because it orbits the Sun, it creates a gravitational field. And there's mathematics that explain how that happens, or describe, rather, how that happens. And there's really nothing to discuss about it. There is no how or why. It's just straight up physics. And so there's a really distinct difference between those two things. Theories are explanations, laws are descriptions.